This is video clip 1, topic 11, multiple regression analysis. In the previous video presentation, we introduced regression analysis using simple linear regression, which is a specialized type of regression that includes one independent and one dependent variable. We want to continue our overall discussion of regression analysis by looking at multiple regression analysis. And so you might want to have available to you the PowerPoint presentation for topic number 11 entitled Multiple Regression Analysis. Now, just to review our introduction to regression analysis, regression is a type of analysis which looks at the relationship amongst variables. It is an analysis in which the direction of the relationship is indicated, just as it is with correlation, but also the magnitude of the relationship. So in other words, one can use a regression analysis to make estimations and predictions about an outcome variable or a dependent variable given our knowledge of one or more predictor or independent variables. In the case of simple regression, we used a single independent variable. In the case of multiple regression, we would use then two or more independent or predictor variables to predict some sort of outcome or dependent variable. And those are examples of linear regression. Of course, there are other types of regression as well, such as logistic and canonical, but we'll be dealing with the primary, but the most commonly used types of regression, and that is linear regression, both simple and multiple. Multiple regression is far more prevalent than simple linear regression. Simple linear regression, you're not going to really encounter much of that in the research, just because simple linear regression kind of presupposes that you have one single variable that acts as a really comprehensive predictor of an outcome, which especially in behavioral sciences, when you're dealing with human behaviors that sometimes are difficult to capture quantitatively, being able to find one single independent variable that can provide a high level of predictability becomes very difficult. So more often than not, you're going to see researchers choosing a variety of variables, multiple variables, to try to establish some sort of predictive model. Again, using a sample to predict out to a larger population. So that's what we're talking about with multiple linear regression. It's a more complicated type of analysis than simple linear regression, but again, unless you are able to find that perfect predictor variable, that perfect independent variable, it's very difficult to try to provide a really good model just with a single independent variable. So that's where multiple regression comes into place. For example, going back to our example with health care costs, yes, we talked about a model in which we might gather a sample and use the independent variable, which was age, to provide predictability of the dependent variable, which might be estimated health care costs per year. And we probably theoretically assume that there's some sort of relationship between age and health care costs, and that's well and good. Very likely, though, one could find that there are other predictive variables that could add to the predictability of healthcare costs. For example, if there's some sort of instrument that's able to look at a person's overall level of healthiness, some sort of healthiness indicator, I'm assuming something like that also would provide predictability of healthcare costs. You might hypothesize that the higher level of good health, then the lower level of healthcare costs. You might see some sort of inverse relationship between those two. And obviously, one also would hypothesize that as age increases, also healthiness might tend to decrease, generally speaking, in the population, although there are going to be exceptions to that, obviously. But those two are probably related to each other, but again, you're probably going to add more predictability to the model, add greater predictability of healthcare costs if you include that second variable. So hopefully that's intuitively making more sense. The problem is with multiple regression analysis, as you start adding variables, especially if you've really got fairly strong predictors to begin with, you're not adding a lot of unique information necessarily with additional variables, and there's a marginal utility effect often. When you start adding 15 variables, it's very difficult to get unique information out of variable number 16 then, because if variable 1 and 2 are highly related to each other, then they're not providing a lot of unique information as far as predicting the outcome variable. That's the issue that's known as multicollinearity, which can be problematic in multiple regression analysis. But generally speaking, if given a choice between predicting a student's level of achievement with one single variable versus their level of achievement with a number of variables, which theoretically we hypothesize will affect achievement, it's better to have the full variable model to try to enhance the predictability of achievement. So again, going then into multiple regression, if you look at page 2 of your power presentation, you see that the definition for multiple linear regression is almost identical to simple linear regression, only instead of one variable, one independent variable, we're looking at two or more independent variables and one dependent variable. In multiple linear regression, just as with simple linear regression, by definition, the dependent variable, the outcome variable, has to be on a continuous scale. If it's a categorical variable you're trying to predict as a dependent variable, then you would need to move into logistic regression. But for linear regression, the dependent variable needs to be on a continuous scale. It needs to be meaningfully scaled as a series of data. The good thing about regression, though, is that the independent variables for linear regression, you have great flexibility of choosing these variables as continuous or as categorical, which is really a nice feature of regression analysis. It's heavily adaptable to different types of independent variables and dependent variables, because again, you can move into logistic regression if the outcome variable is categorical. So again, regression analysis is really, I think, a type of analysis which lends itself to a lot of different types of studies, and therefore I would suggest that you really pay attention to regression and keep it in mind in terms of choosing an analysis for your own studies if you decide you want to use quantitative data analysis as part of your own research. So again, with multiple regression analysis, two or more independent variables. And you can see the model there on page 3. If we're talking about the population, and again, you see different types of symbols being used in different sources, but I've often seen the independent variable in a linear regression analysis as being denoted by the Greek letter mu with a superscript 0. And very often you'll see that used as the notation for a dependent variable in the population. And that simply is equal to a combination of each of the x variables that are part of the independent variable set, which is x1 plus x2 plus x3 plus xk, k being the number of independent variables that you're using. So in the population, any given outcome variable can be seen as being a derivative of a number of these independent variables. And how these independent variables relate, if at all, to the dependent variable is a function of what's called the regression coefficient we talked about under the title of simple linear regression. And in the population, we denote these as beta. So beta 1 times x1 plus beta 2 times x2 plus beta 3 times x3 plus beta k times xk. And of course, adjusted for the intercept of the model, which is the level of u superscript 0 when x is equal to 0. So that would be b sub 0, which is the intercept. So that would be the population model. And then when you're looking at the sample, then we use in the sample the predicted level of the dependent variable, which is denoted as y hat, is equal to the intercept plus b1 times x1 plus b2 times x2 plus b3 3 plus bk xk. So as you can see, it's simply just a matter then of exchanging the population parameters for actual sample statistics that we have. So that's actually how the y hat, the predicted level of the dependent variable, is actually estimated given the sample. And the difference between y hat and y y is equal to all of that plus the residual, which we denote by u, and sometimes you'll see it denoted as e also for error. And the residual is the difference between y hat and y, basically. So if you look at the collective residuals in a sample, what that's referring to is simply the error, the unestimable portion that's not estimated or not predicted by the regression analysis. So that's what that u is there for. It's all of that plus u, as you can see on page 3 of your PowerPoint presentation. And that really refers to the error term, the part that's unpredictable. And we'll continue with that in the next video clip.